Welcome back to Calculus 1. I'm Dr. Jeff Groh. Today we're going to talk about continuity. What does it mean for a function to be continuous? Let me show you some examples of how a function might fail to be continuous. If the function has a vertical asymptote, that's kind of a tear in the graph. Even if the function is defined at that point, it's still going to be discontinuous there because of that rip. It doesn't have to zip off to infinity for that to happen. The function might just have a different limit on the left versus limit on the right. In that case, too, the function's not continuous at this location. But even if the limit exists, the function might fail to be continuous if the function value does not equal the limit value. So that gives us an idea. To define the notion of continuity, we need the limit to exist, and we need the function value to equal the limit value. And that's exactly how we're going to define the notion of continuity. Intuitively, we sometimes think of a function being continuous if you can draw the graph without having to pick up your pen, though that will not be a suitable definition for continuity. A function f is said to be continuous at x equals a if the following three conditions hold. I want you to remember there are three conditions in the definition of continuity. First of all, the limit as x goes to a of f of x must exist. 2, the function value must be defined. So the function actually has to produce an output at x equals a. And thirdly, the limit as x goes to a of f of x must equal f of a. So you don't have the situation where you have the limit existing but the function value being displaced. That won't happen. The function value has to fill that little hole in between the limit on the left and the limit on the right. I want you to notice that in the definition of continuity, a function is continuous at a point, x equals a. This is a pointwise condition. We can expand it to be continuous on a set, but it's continuous on that set if it is continuous at each point in that set. And we'll make that a definition. A function f is continuous on a set S if it is continuous for each x in S. So for example, let's consider the function 1 over x. We know what the graph of this function looks like. It has a vertical asymptote at x equals 0, and it is not defined at x equals 0. In particular, the limit as x goes to 0 of f of x does not exist. Therefore, f is not continuous at x equals 0. the limit does exist everywhere else. If a is not 0, the limit will be 1 over a, which is the function value. Since the limit value exists and equals the function value, f is continuous at every other value of a. Where is this function continuous? It is continuous everywhere except 0. One could also state that as everywhere from minus infinity to 0 union 0 to infinity. I need to give you some important examples. We already talked about the Dirichlet discontinuous function. It was defined to be 1 if x is irrational. I think we actually defined it to be 1 when x is rational, but it really doesn't make any difference. It's 0 if x is rational. So the graph is 0, and it's also 1 at interwoven points. For the irrationals, it'll jump up to 1, and for the rationals, be down at 0. If I choose any number a, whether rational or irrational, no matter what little neighborhood I choose, around a there are going to be points close to 0 and points close to 1, which means the limit as x goes to a, for any a, for the Dirichlet discontinuous function does not exist. That means that this function is not continuous, it is discontinuous everywhere. It's continuous on the empty set. Its set of points of discontinuity is the entire real line. It is continuous nowhere and discontinuous at each point. We can modify this last example a little bit to make it continuous at exactly 1 point. Consider the function f of x outputs x if x is irrational, and minus x if x is rational. This function looks like y equals x for irrational numbers and y equals negative x for rational numbers that are interwoven in between. You can see that in the limit, this function will go to 0. 0 is a rational number. It outputs minus 0 or 0 when x equals 0. The limit as x goes to 0 for this function will be 0, and that will be the function value. Therefore, f is continuous where? Only on the set that contains 0. It's discontinuous everywhere else. This really ought to drive home the point that continuity is a pointwise condition. If a function has a little hole in the graph and is either undefined at a, or maybe has the point value displaced from the limit value, which does exist, then we say the function has a removable discontinuity. You can redefine this point value to fill the hole and make the function continuous. If you can redefine the function value at 1 point and make a discontinuous function into a continuous function thereby, then that's said to be a removable discontinuity. A function f has a removable discontinuity x equals a if, first, f is discontinuous at x equals a and the limit as x goes to a of f of x exists. So you get both the left and right limit to exist and be equal to each other. It's just that the function value is either undefined or the function value does not equal the limit value, violating either steps 2 or 3 in the definition of continuity. We can easily come up with functions that have removable discontinuities. For example, consider the function sine of x divided by x. F of 0 is undefined. Therefore, this function is certainly not continuous at x equals 0. But we do know the limit as x goes to 0 of the sine of x divided by x is 1. We worked hard to prove this. So the limit exists, but the function value is undefined. Therefore, x equals 0 is a removable discontinuity. We can define this function to be continuous by filling the hole. We can define another function g of x to be sine x over x when x is not 0 and 1 when x equals 0. This function has been redefined at one point, and now it is continuous. A function has a jump discontinuity if the limit on the left is different from the limit on the right. We say that f has a jump discontinuity at x equals a if both the limit as x goes to a on the left and the limit as x goes to a on the right exist but are not equal. A classic example of a function having a jump discontinuity is the absolute value of x over x. We've seen that this function is -1 until you get to 0, and then 1 thereafter. So the limit as x goes to 0 on the left is -1, while the limit as x goes to 0 on the right is +1. Therefore, x equals 0 is a jump discontinuity for this particular function. If a function is defined on a closed interval from a to b, but not defined out of that interval, in what sense is it continuous at one of the endpoints? Function f is called continuous on the closed interval ab if it is continuous on the open interval ab. That's fine because you can easily define limits at each of these interior points. The only question is, what do you do at the endpoints? And at a, we have 1, the limit as x goes to a from the right you can only approach A from the right. Exists. 2, f of A is defined. And 3, the limit as x goes to A from the right is equal to the function value. Similarly, as you go to B, you have to go from the left. So we're going to add 3 more conditions. 4, the limit as x goes to B from the left exists. 5, f of B is defined. And 6, the limit as x goes to B from the left of f of x equals f of B. So the only new innovation, if the interval that we are considering is closed, is that at the endpoints we have to use one-sided limits. Let me begin by looking at x squared plus y squared equals 1. This is a circle of radius 1. Well, that's not a function at all. So this isn't really the example. What I want to do is solve for y. If I solve for y, I'll start off with y squared equals 1 minus x squared. And when I take the square root, I get y is plus or minus the square root of 1 minus x squared. The plus part gives us the top semicircle, and the bottom part gives us the bottom and the minus part gives us the bottom semicircle. I'm going to let f be the principal square root of 1 minus x squared. The principal square root does not output negative values. It only outputs non-negative values like this. Now this function is continuous. But where is it continuous? It's continuous on the closed interval from -1 to 1. You can see that the function value is 0 at the endpoints, and as you approach those from the one side that it is defined on, you do get the limit going to 0 at each of those endpoints. So we get continuity on the entire closed interval where this function is defined. It is continuous on its entire domain. One example to give students difficulty, but shouldn't. I'll explain it to you right now. This function is not continuous at x equals 0, but it is continuous on its entire domain. That's because the domain of this function is everywhere except 0. And so since 0 is not even in the domain, it's continuous everywhere within this set. There are some basic theorems about continuous functions that you need to be aware of. Suppose f and g are continuous at x equals a. Then so are the following: f plus g. When you add two continuous functions at a particular point, you get a function that is also continuous at that point. It's pretty easy to see how this proof would work out. You just check the limit of f plus the limit of g is equal to the limit of f plus g. But we already know that. That was one of our limit theorems. Also, since both f and g are continuous at x equals a, their limits are f of a and g of a. But that's equal to f plus g evaluated at x equals a. So we get continuity. Addition does not affect continuity. Subtraction does not affect continuity. Multiplying by a constant does not affect continuity. It's still going to be continuous there. multiplying the functions together does not affect continuity. How about dividing? Well, the quotient will be continuous provided the denominator is not 0. Yes, division has that nasty little problem. It follows immediately from this last theorem that if p of x is a polynomial, then p is continuous on the entire real line, continuous everywhere. This follows because, first of all, any constant is nice and continuous, no breaks in the graph there. If you're looking at y equals x, again, nice and continuous, no breaks. And x squared is just x times x. So if you multiply a function times another function and they're both continuous, then the product is also continuous. So you can see x to the n is going to be continuous in a similar fashion for each whole number n. Therefore, every polynomial will be continuous, and the points of continuity are the entire domain, the whole real line. Also, as a corollary, if f of x is p of x over d of x, and p and d are polynomials, in other words, if we're dealing with a rational function, then f is continuous on all points in the real number set such that the denominator isn't 0. Points where the denominator equals 0 will be points of discontinuity. Where is the square root function continuous? The graph of the square root function comes up like this. It goes off forever in this direction. It is continuous on the set from 0 to infinity, where of course we use the one-sided limit as we go towards x equals 0. What about e to the x? Look at me draw that without lifting my pen. It's continuous on the entire real line, but so is every other exponential function. Exponential functions are the form b to the power x, where b is the base. We are going to assume, of course, that b is greater than 0 and not equal to 1, so that we have a bona fide exponential function. If b is negative, you can plug in numbers like x equals 1/2 and output the imaginary unit, which we are going to ignore in this class, since this is a course on the calculus of real-valued functions of a real variable. So this is going to be continuous on the entire real line. If b is between 0 and 1, the graph will look something like this. And if b is greater than 1, then the graph looks like this. Bases between 0 and 1 give you models for exponential decay, whereas bases bigger than 1 give you models for exponential growth. Of course, b equals 1 gives you a constant. What about log base b? Again, if b is bigger than 1, the log looks like this. And if b is between 0 and 1, the log looks like this. Either way, these are continuous on the set from 0 to infinity, not including 0, because those are the locations of a vertical asymptote. First, a little notation. CAB is the notation for the set of all continuous functions on the domain AB. So, for example, ln of x as a function is an element of the set of continuous functions, in this case, from 0 to infinity. Similarly, the function e to the x is continuous on the entire real line. We'll sometimes express that as c of r. Where are the trig functions continuous? By the ratio identities, we can express all of the trig functions as ratios of either sine or cosine. So let's get an understanding of those first. The sine function is defined everywhere and has a limit everywhere, and the limit value will equal the function value everywhere. So sine and cosine, which is just a translation of the sine function, are elements of c of r. They're continuous on the entire real line. That's not true for tangent. Tangent x is sine x over cosine of x. This will not be continuous anywhere that the cosine function is equal to 0. Well, cosine goes to 0 at pi over 2, and also every pi units thereafter. So tangent is continuous on the set of real numbers except pi over 2 plus n pi, such that n is an element of the set of integers. Check that out. So where is the cotangent function continuous? It's continuous everywhere except where sine is equal to 0. And sine is 0 at every integer multiple of pi. Secant is 1 over cosine. So it will have the same set of discontinuities as for the tangent function. It'll be continuous on the entire line except pi over 2 plus n pi, such that n is an element of the set of integers. Whereas cosecant is 1 over sine of x, it will have the same discontinuities as the cotangent function and will be continuous on r except the set of all n pi, such that n is an element of the set of integers. Evaluating limits for continuous functions is easy. If f is continuous at x equals a, then the limit as x goes to a of f of x equals f of a. That's the third part of the definition of continuity, which means to evaluate the limit for a continuous function, you simply plug the number in. Simple function evaluation. For example, if I want to calculate the limit as x goes to pi over 6 of the sine function, I simply evaluate the sine function at pi over 6. Why? Because sine is continuous on the entire line. So my answer will be 1/2. Where is the following function continuous? We'll define the function as follows. F of x equals, say, negative x squared when x is less than 0, x when x is greater than or equal to 0 but less than or equal to 1, and let's say 2x plus 2 when x is strictly greater than 1. How does this function look? It's an upside-down parabola to the left of the origin. Between 0 and 1, inclusive of both endpoints, it's going to look like y equals x. And this other function is a straight line with y-intercept of 2 and slope of 2. So it will intercept the axis here and then go up at a slope of 2 like this. I think you can see that this function is continuous from negative infinity to 1, not including 1, because while the left limit does exist and equal the function value, the right limit does exist but doesn't equal the left limit, which means that the limit doesn't exist. It's not continuous at x equals 1. However, it will be continuous for x values strictly greater than 1. So, each of these little pieces is a polynomial. So we know just from the beginning it's continuous everywhere except where we've pieced these pieces of function together at 0 and at 1. The only question is it continuous at 0 and is it continuous at 1? To answer this definitively, we need to check out the limit from the left as we approach 0 and the right as we approach 0, and the function value at 0. We have to have both the limit value exist, the function value be defined, and the limit value equal the function value. On the exam, I will give you a problem like this. You need to check all three parts to prove continuity at the only points in question, 0 and 1. So let's get at it. If we take the limit as x goes to 0 from the left for this function, we have to use negative x squared. We next calculate the limit as x goes to 0 from the right. To the right of 0, you have to use the x function, and that also gives you 0. These two together allow us to conclude that the limit as x goes to 0 of f of x equals 0. Finally, f of 0 is calculated by using this function, which gives us 0, and that's equal to the limit Therefore, f is continuous at x equals 0, which you can see literally on the graph. We know it will not be continuous at 1, but I want you to go through these three steps again, just as with x equals 0. For x equals 1, we need to calculate the limit as x goes to 1 from the left. To the left of 1, that's the function x. And since that's continuous, you can just plug that in and get 1. To the right of 1, you have to use this other function, 2x plus 2. The limit there is 4. We see then that the limit as x goes to 1 of this function does not exist. Therefore, f is not continuous at x equals 1. We still have to put together and tell where this function is continuous. We can finally state our answer as follows. it's continuous everywhere except at 1. One of the ways that we have constructed functions is by function composition. That leads us to the following theorem. If g is continuous at x equals a, and f is continuous at g of a, then f composed with g is continuous at x equals a. After all, f of g of x is f composed with g. So x equals a gives you a point of continuity for g. G outputs g of a, and we're assuming that f is continuous at g of a. Then the composition is continuous. When you compose continuous functions, you get a continuous function. So, to give you a simple example, consider the function sine of 1 over x. The outside function f is sine, and the inside function g is 1 over x. 1 over x is continuous everywhere but 0. The sine function is continuous everywhere. So the composition of these two functions is continuous everywhere but 0. For another example, consider the function the square root of 1 minus x squared. The inside function in this case is 1 minus x squared, which is a polynomial. It's continuous on the entire real line. But the outside function, square root of x, is only continuous on x bigger than or equal to 0. That means to find the points of continuity, we have to ensure that 1 minus x squared is in the domain of the square root function. So where does that give you? That gives you x squared is less than or equal to 1. If you take the square root on both sides, the square root of 1 is 1. What is the square root of x squared? The absolute value of x. Be careful with that. It's not x. It's the absolute value of x. Your Algebra 1 teacher told you the square root of x squared is equal to x, but only provided x is positive. They tried to ignore all those nasty little details, but we have to pay attention to them now. The absolute value of x is less than 1, less than or equal to 1, is equivalent to negative 1 is less than or equal to x is less than or equal to 1. That's how you solve these absolute value inequalities. So this ends up being the set of points of continuity. We're in the class of continuous functions from negative 1 to 1. We're now going to present an important theorem that we will use in the remainder of this course. It has a name. It's called the intermediate value theorem. The picture for what goes on here is kind of like this. If you have a function defined on a closed and bounded interval from a to b, and that function is continuous, if you choose any intermediate value between f of a and f of b, say some number k, then there has to be some point c in the domain where f of c takes on that intermediate value k. We'll state the theorem like this. If f is continuous on the closed interval ab, and k is between f of a and f of b, then there exists c. between A and B such that the height at C is equal to this value k. If our function is discontinuous, the intermediate value theorem may fail. You can choose k's so there is nothing that goes back and maps to that height k. So the continuity assumption here is essential. As a simple example of an application for the intermediate value theorem, let's prove that the function f of x equals 2x squared minus 1 has a root on the closed and bounded interval from 0 to 1. Here's our proof. We're trying to prove the existence of some place between 0 and 1 where this function crosses the x-axis. What we'll do is we'll evaluate the function at 0. We'll get negative 1, which is less than 0. And f of 1 is 1 squared is 1 times 2 is 2 minus 1 is 1. That's greater than 0. So we know that at 0 we get negative 1, and at 1 we get 1. Somewhere in between, there's a place where it must cross the x-axis if the function's continuous. But f is continuous on 0, 1, since it is a polynomial, and polynomials are continuous on the entire real line. We deduce then, by the intermediate value theorem, IVT or IVTH, either abbreviation is standard in mathematics, that there exists some point C between 0 and 1 such that f of c equals 0. The intermediate value theorem tells you the point exists. What it doesn't do is tell you where that point is. But setting this function equal to 0 and solving for x is simple enough. Another simple application of the intermediate value theorem is the bisection method for root finding. The idea goes something like this. Suppose you have a function and you know at a it's negative and at b it's positive. Well, you know by the intermediate value theorem that it has to cross the axis someplace in between. But where? Not knowing exactly where, you cut the interval in half. You bisect it at the midpoint. If you get a positive there, then you throw away this b and make this a kind of new b. I'll call it b hat. It's the b that wears a hat. And then you bisect the interval again. If you happen to be negative there, you throw away the old a and give yourself a new a, and you keep bisecting, narrowing down the location of that root to finer and smaller intervals until you obtain an approximation to where that curve crosses the x-axis to whatever degree of accuracy that you need for your particular application. You can see that you can employ this method over and over again, narrowing down the location of that root to arbitrary levels of accuracy, way beyond what you can get on your graphing calculator. The bisection method is great because you know it is going to work. The intermediate value theorem guarantees that you will converge to the solution. The bisection method is terrible because it converges very slowly to the root. So let me give you a basic description of the method again. Let's suppose that f of a times f of b is less than 0. That means one of them is positive and one of them is negative. This doesn't tell you which one is which, it just tells you they have opposite signs. If that's true, and you form the midpoint. The midpoint is, well, it's the average. M replaces either A or B if both the function value at the midpoint and at B are positive, and the function value at A is negative, then you're going to throw away the old B and replace it with the midpoint. Otherwise, you'll throw away the old A and replace it with the midpoint. Let's do an example real quick. Let's suppose we have the function f of x equals x squared minus 2. We know this thing has a root at the square root of 2, which has a decimal representation of about 1.414. I'm going to state that f has a root on the interval 1 to 2. We know this by the intermediate value theorem. If you plug 1 in, you'll get negative 1. If you plug 2 in, 2 squared is 4 minus 2 is 2. You get 2. So it's negative at 1 and positive at 2. Our first midpoint is 1 plus 2 over 2, or 1.5. 1.5 squared is 2.25. Minus 2, you get a positive value. From there, we'll throw away the 2 and assert that the root exists on the interval from 1 to 1.5, which you know is true because the root is 1.414 approximately. We keep on going. The next midpoint is 1.25. And f of that midpoint will be negative. And so you'll have this narrowed down to somewhere between 1.25 and 1.5. As you can see, this will converge very slowly. I should mention that later in the course we will have a method that works much better than the bisection method. It's called Newton's method. So you need to know, however, the bisection method. A lot of numerical schemes that are used in your handheld devices are sometimes use the bisection method as a startup to narrow where the root is initially, and then use a method that converges more rapidly after that.